representing motion. All right, here's our objectives. First, we should be able to describe position and velocity of an object using representations of that object's motion. To meet that objective, we should understand that motion can be represented by motion diagrams, figures, graphs, equations, and narrative descriptions. Graphs of position and velocity as functions of time can be used to find the relationship between those quantities. And an object's instantaneous velocity is the rate of change of the object's position, which is equal to the slope of a line tangent to a point on the graph of the object's position as a function of time. The displacement of an object during a time interval is equal to the area under the curve of a graph of the object's velocity as a function of time. For the calculus students out there, you'll recognize our displacement is the integral of v with respect to t. Some vocabulary. We've got a motion diagram, which is a representation of motion as if a picture is taken at equal time intervals. The distance between each dot represents the distance traveled in that equal time interval. Magnitude just means how big or how much. Position as a function of time, that just means it's a graphical representation of collected data with position on the y-axis and time on the x-axis. The gradient will represent the velocity. This is also known as the derivative. Velocity as a function of time means that we're going to have velocity on the y-axis and time on the x-axis. The gradient is going to represent acceleration, while the area under the curve represents the displacement. Area under the curve just means it's the area between the gradient and the x-axis, also known as the integral. Acceleration is a vector that's going to show up when there's a change in an object's speed or direction of motion. We use symbol lowercase a, and the unit of measurement is meters per second per second. You may also hear this as meters per second squared. So remember that our average velocity is our displacement over time. This can be expanded because that delta, remember, means final minus initial. So let's say we want to solve for an object's final position. We're going to rearrange the equation to get delta x all by itself. To do that, we're going to multiply by time on the right side. If we do something to the right side, we have to do it to the left side to keep that equal sign. Then our displacement equals our average velocity times the change in time, or the time interval. Now we can expand out that delta. The final position minus the initial position equals our average velocity times the final time minus the initial time. Next, I'm going to add my initial position to each side to solve for final position. And I get my final position equals my average velocity times my final time minus my initial time plus my initial position, which is great, but I'm going to rearrange this just to make it look a little bit neater. And I know this bottom line equation can look intimidating, but remember that our initial position a lot of times is 0, so that's going to just be 0. Our initial time usually is just 0, so you can also just have a 0 in there to make your life a little bit easier. Either way, you need to be comfortable with this process. All right, speed is our distance over time. We can't expand the displacement because there is no delta. However, we can still solve for distance traveled after some amount of time. Go ahead and try this problem. Pause, or not pause because perhaps you've done it already and it's just that quick. Notice that I have circled my answer and shown the units. That's how we answer questions in physics. Sometimes it's useful to show motion as if a picture was taken every second, or strobe light going off. This gives a general sense of how the object was moving. For example, we've got a ruler here. And we start every second, there's a position being shown. You can think about a strobe light going off or pictures being taken. just to show where the object was. We also want to include the direction our velocity is. If we're moving to the right, then our velocity is to the right. So we include that into our motion diagram because otherwise it's just a series of dots and it doesn't really tell us very much information. Here there's equal spacing between each dot and the picture was taken at regular intervals. Same distance and same time means that the velocity for each of these time intervals was the same, or we're moving with a constant velocity. We show this with the arrow pointed, yes. Is the ball now moving with a constant velocity, speeding up or slowing down? V equals our distance over time. Time is the same, so it becomes big change in x as we start moving along. Our displacement is getting bigger and bigger. In the very beginning, we had a small separation between the two, and then eventually we had a larger one. I like to rewrite the equation to show which variable increased or decreased by making it bigger or smaller. And because this initial equation is a fraction, if we make the numerator larger, that means our answer is also becoming larger because time is staying the same.
Here's an object slowing down. The equation shows the relationship between the variables with t remaining constant. X is getting smaller, so v is getting smaller. We can also graph this motion by plotting the object's position as a function of time. Because the speed is constant, we end up with a straight line as our regression line. Every second that goes by, the ball is covering a greater distance, which demonstrates exponential growth. The shape of this graph shows acceleration, or the changing of velocity. Because the distance here is getting smaller, with each time interval, the graph would look like a square root graph. Besides reading the graph and getting points, it is very useful to consider the slope of this graph. Here, the slope, remember, is rise over run. So the slope of a position versus time graph means the rise is our displacement and the run is our time interval. Displacement over time is velocity. So we would say the slope of a position versus time graph is velocity. That's an important fact to remember. You need to have it on the front of your brain for the rest of the year. The slope of a position versus time graph is velocity. The instantaneous velocity is the same anywhere along this slope because the slope isn't changing, it's constant. So we can then turn this position versus time graph and take the information and line it up with the very same time intervals and plot all of those velocities. And because our velocity is not changing, we end up with a velocity versus time graph that looks like this. We can go one step further and remember the slope is rise over run. So the slope of a velocity versus time graph is delta v over delta t, which is acceleration. Acceleration is the changing of speed or direction. This slope is 0 and represents a 0 acceleration. This slope is 0, represents 0 acceleration. The acceleration units, because it's rise over run, it's meters per second over seconds, so meters per second, or meters per second squared. Another way to think about that unit, meters per second, is meters per second every second. So the velocity is changing 0 meters per second every second that goes by. Here's that object speeding up again. That was our position versus time graph. Now we have a changing velocity. So now, depending on where we take our slope, our velocity is changing. Acceleration. Change in velocity over time. And again, for our acceleration versus time, we now have a constant acceleration. So even though our velocity is changing, our acceleration is constant. For the object slowing down, the change in displacement or the change in position is getting smaller and smaller and smaller as you go. So that means your velocity is getting smaller and smaller and smaller towards zero. Remember the x, y origin is 0. Here we end up with a negative slope, negative acceleration. Our velocity is going to the right while the acceleration is going to the left. That means our object is slowing down. Whenever you have velocity and acceleration in the opposite direction, the object is slowing down. Whenever you have velocity and acceleration in the same direction, your object will be speeding up. I'm not going to do examples because of all of that information, but the next steps, complete practice problems as prescribed on the website. Here's your AI prompt for this lesson. Provide me with 3 practice problems for graphing position, velocity, and acceleration from a funny given scenario. When you're ready to check yourself, you can then ask what would the graphs look like, and you should get an explanation of the general look. Don't forget to ask each other, ask me, and keep asking until you get it.